Thank you, thank you. So, good morning, everybody. It's now 9 a.m. My name is Ashton Hunter. I'm a content specialist with Peer Tutoring, and yeah. So today we're going to be doing a Physics One camp. I know it's early, but hopefully, this won't be too much. It'll be kind of interesting, and hopefully, I'll be able to give you a good foundation of kind of what you can expect to see in your, initial physics classes. So, yeah, I'm just gonna dive right into it. I know people are still coming in. If you wanna, introduce yourself in the chat, say a fun fact about yourself. In the meantime, I definitely encourage that. So let me pull up my OneNote. Uh, um, okay. Actually, let me see if I can just, well, okay. I'm just gonna assume y'all can see my OneNote now. I can't see the chat, so let me see if I could just share the application. I guess not. Let's bring it down here. So I apologize if y'all ask questions in the chat and I'm not able to see them. Um, but I'm sure one of our moderators will maybe answer, any questions you have in the chat. So, today's camp, I plan on kind of introducing you to the idea of forces. And so, in my opinion, I think a key thing about physics and kind of the difficulty of it is, it's just kind of the language and kind of having a good definition for, these words we often use in physics. And often the words we use in physics, we also use in everyday life, but they don't always have the same meaning. So I just wanted to give you all a good, solid definition of a force. If you read this in a textbook anywhere, the easiest, most simplest definition of a force would be either a push or a pull. Simple as that. And there are basically, it's just a little physics background, but there's basically four fundamental forces, basically in the universe. And what we mean by fundamental forces is that these are forces that kind of just, happen in the background of everyday life. So there'd be gravity, electromagnetism, the strong force, and the weak force. So again, these forces here are just forces that are, always happening in kind of the background of our lives. So gravity is, kind of just always happening. Electromagnetism, strong as well as weak. But for today, the only one of these forces we're really focusing on is gravity. And so basically we know gravity is, this force that pulls things down towards the earth. So this is the earth here. And gravity is basically what, holds all objects onto our rock that we call Earth. And so, um, who else better to start with than Isaac Newton when talking about forces? And so here, we have Newton's three laws of motion, and he basically came up with these in his thesis in 1687. And if you look in a physics book, these will be kind of the technical definitions of Newton's laws of motion. But I'm going to try to read them out to you and then kind of give them more of a layman's kind of terminology. So Newton's first law is that every body continues in its state of rest or of uniform speed in a straight line unless acted on by a non-zero net force. So basically what they're saying here is well, body is just some object. So basically saying an object will continue to be either in rest or in uniform speed unless acted on by an outside force. So the kind of visual that I keep in mind for this first law is if we think about let's say a flat surface that has ice on it, so kind of like a ice ring. So this is ice, and specifically it's ice because ice has no friction, things kind of just slide on it. So if I were to like make this an incline here and put, let's say, a hockey puck on this ice, just kind of set it there, and I let the hockey puck go, the hockey puck will, then slide down and then slide on the ice. And so here, the professor would ask you, what do you think would happen to that hockey puck, this hockey puck here, over a long period of time if it continued to slide on this ice? And he would say, well, some people may think, well, the hockey puck would eventually come to a stop for some reason. But in actuality, since there are no outside forces acting on this ice, the ice would actually continue to slide on this ice here with a uniform speed. So it would basically slide on forever with a uniform speed until, say a person comes and stops it. But otherwise, the hockey puck would slide on forever. And so this is basically Newton's first law, and it's also sometimes called the law of inertia. The second law is probably the most popular one, but it basically says the acceleration of an object is directly proportional to the force acting on it and is inversely proportional to its mass. The direction of the acceleration is the direction of the net force acting on the object. So throughout this whole camp, we'll really be reiterating this second law. Basically what this second law is saying that the acceleration is proportional to the force. So acceleration is proportional to the force and is inversely proportional to its mass. So inversely proportional means, that quantity of mass is going to be on the bottom. And acceleration is a vector as well as force is a vector. So I'll use this notation that, if you went to the vectors camp yesterday, you're familiar with this line, or sometimes it's an arrow, but I'm just going to use a line over the quantity to indicate that it's a vector. So this equation says that acceleration is equal to the force on that object divided by the mass. And another way you can write this, which you'll usually see it as, is force is equal to mass times acceleration. So you can write this equation either one of these ways, but you typically see it in this form here. So let's see. Now the third law says whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. So this one is basically just the law of action and reaction. Same way people always say, every action has an opposite but equal reaction. When this is basically what the Newton's third law says. And to put that into kind of an equation to show you what that looks like, it would be basically force 1 on 2 is equal to the negative of force 2 on 1. Okay, and I'll kind of expand on that once we get down to certain examples. But for now, that's basically Newton's 3 laws of motion. The first one basically saying objects will remain at rest or in motion unless acted on by an outside force. The second law gives you an equation for force and acceleration, or relating force and acceleration. And the third law is, every action has an equal opposite reaction. And so the next thing I kind of want to touch on before we move forward and get into the kind of the more mathematics part is the difference between mass and weight. Because in everyday language, we kind of use these things interchangeably, mass and weight. But in physics, mass and weight have a distinct difference. So I've written here basically mass is how much stuff you have. So by stuff, I mean you could imagine mass as being like how many atoms are, all together inside of an object. So if we have, let's say, a basketball here, something like this, we would say this basketball has a mass of I don't know how much basketballs are there, 3 kilograms. So that would be the mass of the ball. And also note that mass is always measured in kilograms. And so kilograms is a SI unit, which means just standard international. And so mass is always going to be in kilograms whenever you do any kind of physics problem. And force, I guess I'll say that now, is always going to be in newtons. And acceleration is always going to be measured in meters per second squared. So these are what we call our SI units. So if you have any of the units that are, other than kilograms, newtons, and meters per second, you'll have to convert them into these units here. Okay, so back to this mass and weight thing. So mass is how much stuff you have, and weight is a force due to gravity. And the best way that I kind of conceptualize this is if you have this basketball, you can take it basically anywhere in the universe, and it would still be 3 kilograms. Because the kilograms come from how much stuff is inside of this basketball. So when we say a force due to gravity, which is your weight, you could think of that as, well, let me give you the equation for the force due to gravity. So force due to gravity. So I'm going to use this subscript G to indicate this is the force due to gravity. It's equal to the mass of an object times G, which is, G is basically the acceleration due to gravity. And so G on the Earth is basically 9.8 meters per second squared. And so this is the acceleration due to gravity on the planet Earth. If you go to, anywhere else in our solar system, say the moon, this G value would be something different. It would actually be a little bit less. Whereas in some places or some planets, it would be more. But on Earth, and for all our problems that we'll be dealing with today, G is going to be 9.8 meters per second. And so this force due to gravity, this Fg, is equal to the mass of the object times G, which is the acceleration due to gravity. And let me put brackets on that, because this is we're just looking at the magnitude. And so, again, let me just point out the difference between mass and weight. Mass is how much stuff you have, and then weight, which is the force due to gravity. And you also see some people may write this as W for weight, but weight and the force due to gravity are basically the same thing. So if somebody says, what's your weight? That's the same thing as asking, what is the force due to gravity on them? So let's do a few examples then. So now that we have that in mind, I kind of just want to introduce to you something we call a free body diagram. And a free body diagram is basically just a diagram that shows all the forces acting on an object. And let me just check. Okay. So yeah, free body diagram it shows all the forces acting on an object. So since of course we're on the Earth, there's always going to be a force of gravity acting on an object. So here we have this box. It's just sitting on this surface. And since this box is on the Earth, there is I wrote it downwards because gravity pulls in the downwards direction, and its gravity is basically acting on this box here. And so how we do our free body diagrams is we basically just draw a vector representing the force. So let's see. So the first force we know is acting on this box is the force due to gravity. And so starting from the center, we would draw a downwards arrow, and this would be the force due to gravity, Ft. Now, there's also another force that it's not obvious is there, but is definitely there. It's something called the normal force. So something called the normal force. So the normal force is basically a force that comes from an object being in contact with a surface. So this box here is in contact with this surface, and so as the force of gravity pulls downwards on it, there's something we call a normal force that basically pushes back upwards on the box. And I'll write that as Fn for normal force. So again, the normal force just comes from an object being in contact with a certain surface. Now let me show you why that normal force has to be there. So since this box is just sitting there, we know this box is not moving, so we could say the acceleration of this box is 0, right? We could say the acceleration of this box is 0. And so now if we use Newton's second law, which says here that force equals mass times acceleration, we can basically use Newton's second law to solve for some forces or whatever we're looking for. So to apply Newton's second law to this problem here, or to this box situation, I guess so first we should put our system down. So also when doing your free body diagrams, you also have to have some type of coordinate system that you're working on. So if we superimpose our coordinate system here in kind of the center of the box, where the left and right is going to be our x direction, and the up and down is going to be the basically the y direction. And so now if we use Newton's second law, which says force equals ma, and also another way we can write this, which I didn't write it for, is there can be more than one force acting on an object. So most of the time, it's not just going to be a singular force, but a number of forces on an object. How like here, there is basically two forces.
Hey, Ashton.
So another way you can basically write this is as the sum of the forces.
Ashton, can you hear me?
Which is what this capital sigma represents, is the sum of the forces equals mass times acceleration. And so some write it as just the net force, sum of the forces, but this is basically all the forces on the left side is going to be equal to mass times acceleration. So for this problem here, the sum of the forces.
Hey, Ashton, can you hear me?
Charge.
Yeah.
Okay, so for this problem here, the sum of the forces. The sum of the forces, and the only two forces are the normal force, and notice that it's going upwards, and then there's the force of gravity that's pulling downwards. So that's going to be a normal force, and we're going to write it as positive because upwards is in the positive direction, minus this downwards vector of gravity, which is f of g. And that's going to be equal to basically mass times acceleration, which we know this is 0 because the box is not moving. And so now we're kind of left with just, the normal force minus the force of gravity is equal to 0. And so then this basically tells us that the normal force is equal to the force of gravity. And so that makes sense, right? That these two forces should cancel out. And I say that they should cancel out because this box is basically not moving. And so therefore we can say whenever an object is at rest, so whenever the acceleration is 0, we can say the forces are balanced. And so we can say these are balanced forces. And so with that in mind, you can assume if these forces were unbalanced, then that would cause this box to move, which we'll kind of see in this example here. But before I move downwards to that, let me go over this little pendulum hanging here. There. So here I'm drawing a free body diagram for this hanging ball, where basically this ball is connected to this rope here, and then this rope is connected to kind of a ceiling right here. And so again, if we do our free body diagram, when gravity is always pulling downwards. And so we have the force of gravity pulling downwards on this ball. And since this ball here is connected to this rope, there's another force that we call a tension force that is basically inside of this rope that's kind of just holding the ball up there. And so there's another force upwards. Here I'll write it as Ft for tension. And so here, similar to the box equation or to the box scenario, this force of tension and this force of gravity are basically going to balance each other out such that, so that the ball doesn't move. Just how like here the boxes are moving. So we have this normal force and gravity balancing out. Here we have the tension and the force of gravity balancing each other out. So that's kind of the general idea. Well, these are kind of easy examples of a free body diagram. We'll just basically write our forces and we put a coordinate system down, and we just add and subtract our forces along the coordinate system. Okay. Let me try to move some of this. Move this, shrink it a little bit. So here I have basically another example. So throughout this whole camp, I kind of just have example after example. And hopefully, throughout these examples, I kind of just introduce to you how we use, Newton's laws and all that. So here in this problem, we have this box here again. And now we have two external forces, force 1 and force 2, where force 1 is 10 newtons and force 2 is 15 newtons. And the mass of the box is 20 kilograms. And I wrote the newtons with brackets around it, not for no particular reason. Sometimes I just like to box off the units so it doesn't mix up with the numbers. But outside of that, there's no reason why there's brackets around the units. It's just personal preference. Okay, so we want to find the acceleration of this box where there's these two forces acting on it. All right, so let's do our free body diagram. And instead of doing a free body diagram directly onto the box, I'm actually going to do it off to the side here. Let's first put the coordinate system down. So this is the coordinate system we'll be working on. And whenever we do a free body diagram, we can kind of condense this object or this box down to a point, which would be the center. Actually, that's not. So the center of this coordinate system will basically represent the box here. So it's been condensed down to this tiny point here. And now we can draw each of the forces on it. So first I'm going to draw the force of gravity going downwards, where the force of gravity is given by this equation of mass times gravity. And then there's the normal force, of course, upwards that comes from the box being in contact with the ground. Okay, and now we can just also include the outside two forces that are, also acting on this box. So I'm actually gonna draw it this way. Draw it this way. So this is force 1 here. I just put it onto this side because it's pushing towards the right. And again, since these are vectors, we can kind of move them around, as we please, as long as we maintain, the angle and direction of the vector. We can move it around in kind of any which way. So I have force 1 over here, or force 1 is equal to 10 newtons. And force 2 then, so just pushing to the left. It's going to the left here. Let's make it a little longer. So this is force 2. Okay. So far so good. Hopefully this isn't too bad. But now we're pretty much done. And this here would be our free body diagram for this box here. And so now, if you were asked the question, how many forces are acting on this box, what would you say, the number is? If you can answer that in the chat for me, how many forces are acting on this box? Not a trick question at all, just wondering. Okay, so hopefully you said there's 4 forces, because obviously there's the normal force upwards would be one force of gravity downwards, which is another force, and these 2 applied forces on both sides of the box. So there's a total of 4 forces acting on this box here. So now let's go ahead and see if we can find the acceleration of this box. So another thing that I didn't mention before, but I'll mention it now, is Newton's second law. While it looks simple, this equation here, while it looks simple, it can actually be expanded into, basically 2 different equations, or maybe 3, depending on, the problem. So notice that these are vectors, right? And whenever we add and subtract vectors, they basically have to be along the same axis. So, of course we have this way as the x direction, and up here as the y direction, right? And so basically we're going to use Newton's second law for the x direction as well as the y direction. So then this equation here kind of expands into being this. So now we have the sum of the forces in the y direction equals mass times acceleration in the y direction, as well as the sum of the forces in the x direction. Okay, so we'll use basically Newton's second law for the y direction and the x direction. And notice basically here for this first example, the forces were only along the y direction. So I didn't necessarily make, that distinction here, nor here where the forces are all along the y direction, which is the up and down. And so for this example, we have these forces in the y and these forces in the x. So let's go ahead and do the sum of the forces in those directions. So starting with the y direction, which would be similar to the kind of first example I did, we have the sum of the forces in the y direction. And so this basically just means adding up all the forces that are along this y-axis. And so we have the normal force upwards, the normal force is upwards, and then we subtract gravity because it's pointing in a downwards direction, right? Ft. And since this box, we can basically assume, and we actually know that it's not going to be moving in the up and down direction, right? If you push these box on the left and the right side, there's no reason why it should be going up or down. So we can say the basically the acceleration for the y direction is 0. So it's be mass times acceleration in the y direction. But for the y direction, the acceleration is 0. And basically it shows us again that the normal force and the force of gravity are balanced. Kind of similar to here, how the acceleration is 0, so it showed us that the normal force and the force of gravity basically just balance out. Okay. So now let's do the sum of the forces for the y direction, or this up and down direction here. I mean, for the x direction, let's do the x direction. So sum of the forces for the x direction, there's this force 1 to the right, so it's going to be positive, force 1, and then force 2 to the left, which is going to be negative. So negative force 2, and that's going to be equal to mass times acceleration in the x direction. So finally, now this is the acceleration that we're trying to solve for. We want to know basically how fast this box is going to accelerate due to these two forces. And so just kind of looking at it, you can make the assumption that basically this box is going to end up moving to the left, right? And we can assume that because this force on this side is greater. So just kind of by logically seeing these numbers, we could say, well, force 15 is greater than force 10. So overall, this box should move to the left. It should move to the left. So let's see if that works out here. So let's put in the numbers for force 1 and force 2. So force 1 was 10. So now we have 10 minus 15. And that's going to be equal to, let's see, the mass of the box, I said was 20 kilograms. So 20 kilograms acceleration in the x direction. So now just kind of going through the algebra, subtracting 10 and 15 gives you negative 5. Dividing by 20, let's see, that gives us an acceleration of negative 1/4. Right, and that's going to be meters per second squared. And so now we basically have the acceleration, and we see that it ended up being, this is a vector, ended up being a negative number, where basically that negative just indicates that this box will indeed be moving to the left. Alright, so here is basically another example I have of just a box, and here is just a singular force. And I'm going to try to speed this up now a little bit. I guess I took more time than I thought, kind of explaining some things. but hopefully you kind of get the general idea of this free body diagram and summing up the forces. So here, this is going to be a top-down view. So this is basically the top of the box here, and we're looking kind of down at it. And so since this is a top-down view, and this is our force here, a force of 10 newtons, and now it's at this angle of 30 degrees with the horizontal, how they would say. So of course, first thing you want to do is draw your free body diagram. So let's see. Draw a coordinate system here. And here is our force. I'll put it at an angle. So this is our force. And it makes an angle of 30 degrees. Alright, cool. So basically kind of what I want to show here is how we kind of break this force into X and Y kind of vectors or components, they say. And so here again, we're not worried about the force of gravity or the normal force, because this is a top-down view. And so let's see, kind of imagine it this way. And we're looking kind of down on the box there like that. So I'm calling the upwards the Y direction. This is the Y, it's called this the X. Keep it simple. So now we just want to basically find the acceleration. Well, actually, what I kind of want to show you here is how we break this force into X and Y components. And I think we kind of went over this in vectors yesterday, but just to quickly recap, this is our force here. It has a magnitude of 10, right? So you can imagine that as the hypotenuse, and we know our angle there is 30 degrees. And so we can basically project this force onto the Y and onto the X direction. So the force in the Y direction, we'll start with the X direction. This would be the X component down here. If you project it downwards, now you can imagine this makes a right triangle. And then this down here is going to be the X component. So I'm going to put a little X next to this force. That would be the X component of this force. And so to solve for that using SOHCAHTOA, let's see, SOHCAHTOA. And so since this is the adjacent side, adjacent to the angle, we're going to use basically COS. And the cosine, it basically says cosine theta is equal to adjacent over hypotenuse. So cosine theta is equal to the adjacent over the hypotenuse, where the adjacent side is this X component of the force, and the hypotenuse is basically the magnitude of the force, which is 10. So kind of putting all that together, we see that cosine, and the angle is 30 degrees, so I'll just write 30 is equal to the adjacent side, which is the X component of the force. divided by the hypotenuse, which is basically the magnitude, which is 10. So I'll just put that in. Right? So now we can solve for the x component of the force, which is just going to be equal to 10 times cosine of 30. Right. And so kind of using that same methodology, we can also find the y component of that force as well, which would be over here. And so for the y component, we see it's the opposite side. I'm kind of speed up here. This is basically a vector analysis kind of. So the opposite side would be for sine theta. And so sine theta, or sine of 30, because that's the angle, is going to be equal to the y component of the force divided by 10. And that gives us the y component is equal to 10 times sine of 30. Okay, cool. So now let's move on to a problem to show why I kind of introduced that. So here, similar box, it's a top-down view. Now there's two forces acting on it. So you can imagine there's one person pulling it this way at 30 degrees, and there's another person pulling it this way at also 30 degrees, but at 5 newtons, and this one's at 10 newtons. And so now let's find the acceleration of this box. So again, first we want to draw our free body diagram. Let me just check the chat. The problem like the one was presented that we always have to find the x and the y force. So for this example here, we have to find the x and the y force. To find the acceleration, we could have just basically, well actually, yeah, because we want to find the acceleration in the x and the acceleration in the y direction. So for this problem, to find the acceleration, you would have to go and break this force into components. So this one is, I think, a better example to kind of show why we have to break these forces into their components to find the acceleration. So first, let's do our free body diagram. And I'm actually going to draw two of them. So of course, we have to do our coordinate system. And we have, and again, this is a top-down view. So this is the top of the box, and then there's, people pulling it at those angles. So we don't have to worry about the force of gravity. So let's put our forces on there. We have one force this way, and we have another force this way, where this is force 1 and this is force 2, right? So now, in order for us to use Newton's second law, we have to break these vectors into their components and then add them and subtract them along their respective axes. So we see, since both of these vectors are the angles, they both have x and y components. So let me draw the free body diagram again, but with those forces kind of decomposed. So force 1, of course, is going to have an upwards one. So it's called this here. This is basically force 1 y component. And so this is basically this here. It's the y component of force 1. And then force 2 is also going to have a y component. So let's say this is force 2 y component, right? Because force 2 over here is also going to have a y component that's upwards. And so now these are our two, force 1 and force 2, they're y components. And let's do the same thing for their x components. So there's going to be a x component down this way. So this is force 1 x component. And so now you can kind of see, of course, there's going to be a x component, but in the opposite direction for force 2. This is force 2x. Okay. So now we kind of see our free body diagram has all its forces along the x and the y direction now. Right. So now we can basically use Newton's second law and just sum up those forces in this upwards direction and in this left and right direction. So let's go ahead and do that. So this force 1y is basically the y component of force 1. And the y component, since it's the opposite side here, it's going to be using what? It's going to be using sine theta. So force 1y here is going to be equal to, it's going to be equal to 10 times sine of 30. Right? And so for force 2 of y, it's going to be similar, but instead of 10, it's going to be 5. So for force 2, the y component is going to be 5 times sine of 30. And then, of course, for F1 in the x direction, it's going to be 10 cosine of 30. 10 cosine of 30, right? Because the x direction is the adjacent side, this side here, so it's going to use cosine. And for force 2 in the x direction, it's going to be 5 cosine of 30. Okay, so now basically what we've done is we took our forces, put it on our free body diagram here, and then took those forces and broke them into basically their components along the y and along the x direction. And so now, using Newton's second law for the x and the y direction, so we have the sum of the forces in the, let's start with the x direction. So looking at the x direction here, you have this force 1x. So we have force 1x and force 2x, which is pointing in the opposite direction, in the negative direction. So it's going to be negative force 2x. And that's going to be equal to the mass of the box times the acceleration in the x direction. And so then we can just put in, so we found out what the components were. So we can put that in. So we have 10 cosine 30 minus 5 cosine 30 equal to mass times acceleration. And from there, you can basically solve for what the acceleration in the x direction is where the mass is 20 kilograms. And so after we've done that, now we can also find the acceleration in the x direction, different color, or in the y direction, I mean. So sum of the forces in the y direction. So we see in the y direction, the two forces are pointing upwards. So we're going to have force 1 y plus force 2 y, where they're being added because again they're both pointing upwards. And so putting in those components, we have 10 sine of 30 plus 5 sine of 30. And that's going to be equal to, again, the mass times the acceleration in the y direction. So now that this is all kind of semi-done, you'll just put in the numbers with your calculator, and you can solve for the acceleration in the x and the acceleration in the y direction. And so notice they ask us to find the acceleration, but it seems like we have basically two answers for the acceleration, one in the x and one for the y. And so that's because basically as these two people pull on this box, it's gonna accelerate at an angle. And we can kind of see which direction it's gonna go by, we can visually add up these vectors, right? By doing a head to tail method or the parallelogram method. So if we were to do that, let's see, let me get an arrow here. And so if we were to add these vectors up kind of visually, it would look something like this. You have force 1 kind of pointing in this direction. That's force 1. And then force 2, which is a little bit shorter, and it's pointing in this direction. So this is force 2. This is force 1. And so force 3, which would be the resultant force, well, it's supposed to be a 1, which would be the resultant force from adding up these two vectors, would look like this. We'd go back to kind of where we started here and point the vector in this direction. So this kind of be our force 3, or force 3 is basically the sum of force 1 and force 2. And so we kind of see here that force 3 is at this angle. Well, yeah, it's at some angle. And so basically, we can imagine this box here being pushed at this angle of force 3 in that direction. And so let's see. I guess I'm gonna leave it at that and try to move on. But basically what we did was we found the acceleration, which is going to be these two components. And so the acceleration, which is a vector, is going to be, we can write it this way, right? We can write vectors as kind of, I guess, coordinate representation. I don't know what they call this. And so see our acceleration is going to have this x component and this y component. which is going to be given, after solving both of these here. And so let's see. I think I'm going to skip this example and let's go through this example here. And so this is just a question I got out of the textbook, just so you can kind of see, how some of these problems might be worded. Where this problem basically says a 750 Newton force acts in a northwesterly direction. A second 750 force must be exerted in what direction so that the resultant of the two forces points westward. Okay, so whenever you go through kind of these word problems, the first thing you want to do is try to draw a proper representation of what they're basically asking. So let's put a coordinate system down. Okay, so here's our coordinate system, and then there's a 754th that acts in a northwest direction. So this is north, south. So this would be west over here. And so this force acts in a northwest direction, so it must be acting directly in between the north and the west. Like that. And when I say directly in between, that means we can basically assume that this is 45 degrees here, and of course 45 degrees over here. Okay, so that force has a magnitude of 750. Cool. So now it says there's a second force must be exerted in what direction so that the result of the two forces point westward. So let's just call this force 1. Let's call that force 1. And we want some resultant force to give us a vector that points directly westward. So we want the force to point basically this way. And I'll call this force 3. We don't know what direction force 2 has to be in. Okay. So just kind of looking at it here, and kind of understanding how vectors work, we know that, this force 2 here must be pointing in this direction some kind of way, right? And I say that because let's say the force was, you know, let's say force 2 is in this direction. If force 2 was in this direction, it wouldn't really make sense as to how, the resultant force would end up being this way. So we know it can't be pointing that way. So if we assume it's pointing this way, this just looks like, it basically cancels out with force 1. So if you add force 1 with this force 2, there's no kind of visual way you can see how it would give us this force 3 here. So we know it's not going to be that one. And so you can kind of deduce that, well, force 3 must be kind of in this direction here. because you can kind of see if we add up these two vectors kind of with the parallelogram method, it gives us kind of that third vector. You know, with a parallelogram method is when you draw a parallel line this way and another parallel line this way, and then the third vector basically goes from one corner to the other corner. So you can kind of see how that kind of works out there, even though my picture is not too good. So now it says, in what direction must this force 2 be pointing? So when they ask for the direction here, they're basically asking for what angle must force 2 be pointing at. Alright, so now let's kind of do our Newton's second law. No, actually we don't have to. Let's just let's just add up these forces, right? So if we kind of look at force 3, this resultant force, we see that it basically has no y component. So like going in the up and down y direction, it has no component. So let's go ahead and like break these vectors into their, kind of write this in component form. So we can write this as like f1x, comma f1y, f1 is f2x, f2y, and let's see, f3 x, f3y. So I basically just rewrote this addition of vectors in this form here. So plus, plus, and equals. Because we know whenever we add up vectors, we have to basically add up their components, right? So we're basically adding this f1 x component with this f2 x component to give us this f3 x component. Okay, so I guess then the next thing we can kind of deduce from this picture here is that the y component of f3 must be 0. So this y component here of f3 must be 0. So this here must be 0. And again, we know it must be 0 because it says that the resultant of the two forces points westward. So it points directly west. So kind of with that in mind, since we know the y component is 0, let's just look at adding up the y components. So we end up with f1 y component plus f2 the y component is equal to basically 0, right? And so now we can basically solve for what this y component must be. So f2 the y component must be equal to the negative of f2y component. Cool. So we kind of see here that the f1y component is going to be equal to the negative of the f2y component. And so what was the f1y component? well, go to our diagram here. Here is our F1, and so the Y component would be well, we'd have to project this vector here, this force 1 vector right here. So this is our F1 Y component. So that's going to be actually the adjacent side, right? Because this side is adjacent to the angle. So that's going to be 750 cosine 45. So the F1Y component is 750 cosine of this angle. And so this tells us that force 2 Y component is this same thing, but the negative of it, which makes sense. So it's basically saying that this Y component downwards, that F2Y, so F2Y is negative, so it must be pointing downwards. And it has this same value of 750 cosine. So this is F2Y. And so finally, all this to kind of show that force 2 must be pointing basically this direction with 45 degrees. And so that kind of makes sense, because if we have a force upwards this way and a force downwards this way that have the same magnitude, then basically the up and down parts, or the Y components, would cancel out. It's basically this Y component up here cancels out with this Y component down here. So since both of those components cancel out, we're only left with the components in the X direction adding up. Okay, so next, and so lastly, I guess I'll go through this example I have for you guys to do, and I'll try to wrap it up there. I'm not sure why this is moving around with that. Okay, well, try to ignore. I don't know why it's moving around like that. So basically, this is kind of an example I have for you guys to do. It should be kind of straightforward based off of everything we talked about here. But the question is, there's two different questions. There's two forces, F1 and F2, shown in both of these figures, where here the two forces are perpendicular, and here the two forces have an angle of 120 in between them. And it says, let's see, we're looking downward, so it's a top-down view. And it acts on a 29 kilogram object on a frictionless tabletop. So force 1 is 20.1. I'll try to get this to stop. I would say a little thin. I heard that you see something like this. Okay. Yeah, sorry that that's moving around with it. So here's kind of a question I have for you guys to do. So force 1 is 20.2 newtons. Force 2 is 26.0 newtons. Find the net force on an object and its acceleration for each situation. So I will kind of work through part A here, and I'll let you guys kind of work through part B, and I guess y'all like 5 minutes to do that, since it's 4 minutes till 10:20. I wish I can stop this from moving. Oh well, just gotta deal with it. Zoom out. Okay, so here is the problem. So again, we want to find the net force and the acceleration for each situation. So I kind of want you guys to work on this one here, part B. And while you guys work on that, I'll try to walk through part A. And the part B will basically be a similar process. So it shouldn't be too hard to do, hopefully. So for part A, we see we have these two forces here, they're perpendicular. So let me just redraw our diagram over here. Okay. Okay, so we have these two forces, they're perpendicular, force 1, and see force 1 is a little bit smaller, so I'll draw it shorter. Force 2 goes down this way. So again, first to find the net force, we know we have to add up our forces with their components. So basically, the net force is going to be the force net, I guess you can write it this way. Is going to be equal to force 1 plus force 2. And of course, since these forces are vectors, we have to add up their components. So for part B, the part you should be working on, we see force 1 only has a y component, whereas force 2 has a y component, and force 1 has a x and a y component. So for this one, part A I'm doing, let me rewrite our vectors this way. We can say force 1 for part A is let's see, it's going to be negative 20.2 comma 0. Alright, because it only has that y component, and force 2 is going to be 0 comma negative 26. Alright, so then to get our net force, then we can just add up the components. So force net is going to be, you kind of just adding downwards. We have negative 20.2 comma negative 26. Okay, so now this is our net force. Our net force is going to be negative 20.2 comma negative 26. And if I want to kind of draw that out, I'll draw it out over here on this. It's going to be negative 20 in the x direction and negative 26 in the y direction. So kind of like here, down here. So this is our force net for part A. And for part B, Just kind of looking at it, I could tell your net force is going to be something like this. Something like that in that direction. So for part B, you should get basically a positive x and a positive y component. Whereas for part A, you get a negative x and y component. So for part A now, find the net force on each. So this is our net force now. The question doesn't specify, but if it did, we can actually find the magnitude of our net force, because this is just the net force for the x direction and the net force for the y direction. So of course, if you want to find the magnitude of the net force, we would do basically Pythagorean's theorem, where we take the square root and we square the x and y parts. So the magnitude of our net force is going to be the square root of negative 20, negative 20.2 squared plus negative 26 squared. And then that would give you the magnitude of the net force. I don't have my calculator, but that would be that part. And let's see, the next question was find the acceleration. So now since we have the net force, we can actually go back to our Newton's second law, which says the sum of the forces. And again, the sum of the forces is also the same as the net force. So you can also write that as force net. These two things are basically interchangeable. Sum of the forces, net forces, both the same thing, is equal to the mass times the acceleration. And so now that we have the net force here, and we also know the mass is 29 kilograms, we can solve for the acceleration. And so the acceleration is going to be force net divided by mass. Um, 29. Cool. So let's see, we have about 5 more minutes left. So I guess with these last 5 minutes, I'm just going to try to recap a little bit instead of going any further. So for part B, I'm not going to I'll work out a little bit of it, just so y'all can kind of double check y'all's answers. So for part B, let's write both of our vectors here within their component form, kind of like how I did here. So we have force 1 we see is at some angle here, so we have to break it down into its components, right? So to do that, we actually have to know what this angle is. So not the whole 120, but this angle that force 1 makes with the x-axis. And let's see, so since this is 90, that's right angle, 90 minus 120, that gives us 30 here. So force 1 makes an angle of 30 degrees. And so the x component, which is pointing in a positive direction, is going to be let's see, it's going to be 20.2 cosine of 30, right? So that's what you should have gotten for your x component for force 1. Then the y component, which we see is going to be pointing downwards. It's going to be pointing downwards like that. So the y component, it's going to be negative 20.2 sine 30. Okay, and then force 2, which is a bit easier because it only has a y component. So force 2 is going to be equal to 0, comma, positive 26 because it's pointing upwards. Okay. And so now from here, we can just add up our components by just kind of adding our x's and adding our y's. So once you do that, you'll get your net force, which is going to be 20.2 cosine of 30, comma, 26 plus, well, 26, well, actually I wrote all that wrong. It's going to be negative 20.2 sine 30 minus 26 or plus 26. So now this is our x and y component for the net force. Then we want to find the magnitude of that net force, which is going to be the square root of the x and the y component squared. So I'm just going to write it like this to shorthand it. The force net x direction, x component squared, plus the net force y component squared, which is all these up here. And then from there, we can find our acceleration. So you should have gotten something like that for part B here. And so now it's 10:28. Yeah, so that's pretty much the end of this camp. Tomorrow I'm going to be going over kinematics, or the laws of motion, or equations of motion, I should say. Which I think is maybe a little bit harder than this, but you know, it won't be too bad. So just kind of recap. So today we talked about forces, um, went over Newton's laws of motion, where the first law just says any body is gonna remain at rest or stay in motion unless acted on by an outside force. So it basically means, uh, yeah, there has to be an outside force or unbalanced forces acting on an object in order for it to either speed up or slow down. The second law, which just gives us this equation here that says the sum of the forces are equal to the mass times the acceleration. And the third law, which we didn't get too much into, but it basically says every force has an equal and opposite force. And then we talked about the difference between mass and weight, where mass is basically how much stuff you have, or like think of it as how many atoms, or you could think of it as, if you take this basketball to the moon, it would still be 3 kilograms. But the main difference about the Earth and the moon is this force of gravity here, or this acceleration due to gravity, they call it. And so the acceleration due to gravity is more on the Earth than it is on the moon. So this ball would weigh less. It would weigh less on the moon, but it has the same mass, no matter where it goes. Then we talked about free body diagrams, which are just these kind of vector diagrams where we apply all our forces. So like here we have this normal force and force of gravity, where here the forces balance out. For this problem, the forces are going to the left and the right. So this is our free body diagram. And basically based on these free body diagrams, we break our forces here into X and Y components so that we can add them up. So like for this example, or for basically this last example we did, we have to take our forces, break them into X and Y components, and then we can add them up to find our net force. And then once we find our net force, we find our acceleration. So that is, I guess, an introduction to forces, free body diagrams, and I guess kind of an application of vectors that you kind of saw yesterday. So with that, it's 10:32. And before you guys leave, I'm gonna drop a survey into the chat. I don't know. And let me just stop the recording.